Given the information provided, is triangle ABC similar to triangle DEF? Remember, that sign, the squiggle sign, means similar. Let me tell you what I start to notice. I see these two triangles look similar. They have one angle in common. I'm marking that here in green. It's a 39-degree angle in both triangles. I also notice there are two pairs of sides that appear to be proportional, but I don't know anything about the other two angles. Are their measures the same? And because I do not know the third side in both triangles, I am not certain if it's really the same ratio. Let me write down what I do know. I'm going to translate the small triangle onto the larger triangle in such a way that I align that common angle measure of 39 degrees. It looks like I can do that just using a vector from D to A, and it's going to look something like this. I'm much more convinced now that these two triangles are similar. I see two lines, and I am pretty sure that they are parallel. Lines EF and BC. Why do you think I say that? That's right. The fundamental theorem of similarity. I might be able to use that here. I see a picture that looks just like what we did when we were studying that theorem. I know that I have proportional sides on either side of that triangle. So I have the longer side 2 compared to the 1, and on the other side I have the 6 compared to the 3. They have the same scale factor comparison. It's 2 in both cases. If that's the case, then I have a dilation that would map E onto B and F onto C, both with respect to that center D or A, depending on how you want to name it. And if I do that, I know that when I dilate 2 points from the same center, the segments between the original points will be parallel to the segments of their dilation. And I get the same scale factor on the third side. I've established my similarity. But wait, did I check the rest of the angles? What do you think? How could I show that the other two angles in my triangles that I do not yet have a check for are also similar? When we cut a set of parallel lines with a transversal, it told us certain pairs of angles were congruent. Can you see a pair of congruent angles? That's right, we actually have two pairs here. I notice we have the angles AEF, and we also have the angle with the same measure that corresponds to it on the lower line, angle EBC. These are both congruent angles, and they are cut by that transversal that goes through the points E, A, and B. On the other side, we similarly have two pairs of congruent angles because they are cut by the same transversal. That's AFE. And what angle would I write congruent to angle AFE? Type it in the chat. That's right, great job. It's this lower angle that I've also marked in orange from when I translate the angle AFE along the ray onto the lower line. And those both happen to be congruent, therefore they have the same measure as well. All right, so let's recap. We started with one angle that was known, that was common to both triangles, and two pairs of sides in both triangles that formed that angle. And what we knew about them was that they were also proportional. Using this, we were able to use the fundamental theorem of similarity to say, oh, we have parallel lines. And from there, that gave us corresponding angles so that we could use the angle-angle criterion. So this gives us what we call the side angle side criterion for determining triangle similarity. When we have two triangles with this one angle of equal measure, where the lengths of the sides that form that angle happen to be proportional in the two triangles, we know they are similar. Let's look at this example. We have a triangle ABC, and then the larger triangle AB prime C prime. Given the information provided, do you think these two triangles are similar? Type your thoughts in the chat. I am thinking no. The reason I say no is I look at two sides and I notice they don't appear to be parallel. The way to prove this is by using the word that I highlighted in bright red in my side angle side criterion theorem. Because if these two triangles were similar, then the ratio of all corresponding sides would have to be the same so that I had the proportionality. So I look at side AB's length and AB prime's length. That's 4.9 and 8. Consider what the ratio is between those two sides. This means I want AB prime divided by AB, those lengths, 8 divided by 4.9, to be equal to the ratio of the other two known sides. So I want to keep the bigger sides in the same triangle together. So AB prime was on top, so I'm going to have AC prime on top in the other ratio as well. That's because those come from the same triangle, divided by the length of the side that corresponds potentially in the smaller triangle, AC. That ratio is 7.1 divided by 2.7. There are two ways I can answer this question. The first one is do the two divisions, compare the answers I get. I have an alternate system I can use that you may remember from your work in proportions. So to answer the question, remember that if I have one number A divided by another number B is equal to a second ratio or fraction, C divided by D, that statement is equivalent to saying the following: A times D is equal to B times C. We call this the cross product way of understanding or solving a proportion. It gets its name because when we go through this process, we do it by multiplying across on both sides. So we'll do two multiplications. So what we end up with is the product of that numerator from the left times the denominator on the right, and setting that equal to the denominator on the left times the numerator on the right. There's the cross product. To check that whether 8 divided by 4.9 equals 7.1 divided by 2.7, I'm just going to multiply across. So first I'm going to compare, does 8 times 2.7 happen to equal 4.9 times 7.1? Now 8 times 2.6 is 21.6, but 7.1 times 4.9 is 34.79. Those two quantities are not equal. And because the cross products are not equal, I can conclude that my original proportion, the ratio of those two sides pairs, are not equal. Well, if the two side pairs are not proportional, then these are not similar triangles.